Good morning, everyone, and thank you for coming to the first keynote lecture of the conference. Our speaker, Prof. Corotis, is the Denver Business Challenge of Engineering Professor Emeritus at the University of Colorado, Boulder. With 3 degrees in civil engineering from MIT, he served on the faculty of Northwestern University, established the Department of Civil Engineering at Johns Hopkins University, and was the Dean of Engineering at the University of Colorado, Boulder. He has performed groundbreaking and discipline-defining research in structural safety and reliability, and on the coordinated roles of engineering and social science in framing and communicating long-term hazard risks and resiliency for the built environment. Consequently, in 2002, he was elected to the National Academy of Engineering. Professor Corotis has chaired committees on structural safety, both for ASC and ACI, as well as the Executive Committee of IASAR, served as science advisor for the Department of State in Washington, D.C., and was editor of the Journal of Structural Safety and our own Journal of Engineering Mechanics. For the National Academies, he served on the Building Research Board, the Disasters Roundtable, the Board on Infrastructure and the Constructed Environment, chaired the Laboratory Assessment Board, was the founding chair of the Committee on NIST Technical Programs, and served as chair of the Civil Engineering section of the National Academy of Engineering. He is a registered professional engineer and structural engineer, a distinguished member of ASC, a fellow of the Structural Engineering and Engineering Mechanics Institutes of ASC, and recipient of multiple awards. I will just mention a few here: the ASC Walter Huber Research Prize, the Shinozuka Medal, and the Opal Award, and is the author of more than 250 technical publications. It is a distinct honor, a unique privilege, and an immense pleasure to introduce one of the preeminent leaders in the fields of structural safety and reliability, probabilistic code formulation, societal trade-offs of risk and natural hazards, and policy decision-making, Professor Prof. Corotis.
Thank you, George. It was very nice. I was at a meeting in Los Angeles once, and the fellow got introduced, and he came up and he said, "Boy, that was exactly how Mama wrote it," so I appreciate it. So it is an honor, of course, and a pleasure to be here, my old hometown. I was at Northwestern University for a number of years. It's interesting to hear Dean Bragg talk about the collaboration among universities. So what I thought I'd do today is talk on 4 somewhat different aspects of engineering risk analysis and disasters. And my research has gone from very narrow to very broad throughout my career, and I'm going to try to touch on different aspects of that. Before I start with that, I want to give a little history. As Arif said, in 2008, the EMI was formed. Before that, it was the Engineering Mechanics Division. But actually, in October 1 of 2007, we were tasked with preparing for it. And we had to come up with a symbol, because ASCE required that. And the structures, of course, has a bridge. Geotechnical, probably due to Stein Stewart here, a beautiful cross-section of soil and earth. The Construction Institute has a hard hat. So what were we going to do for EMI? I mean, we don't just show a bridge or a dam. So I said, well, we are definitely the most mathematical of the institutes of ASCE, so we should do something to represent that we form the mathematical basis for all of ASCE. So I said, let's do an integral. And they said, well, that's nice, but we have to hire a professional firm to come in and pay them $10,000 to come up with something that's better. And after they spent the $10,000, we said we liked my integral best, so we stuck with the integral. So I'm kind of proud of that. The interesting thing is, we originally, was it going to be a definite or indefinite integral? Of course, we want a definite integral. So we need a lower bound. So we picked 1687, which was the year that Newton published his Principia, which is considered the foundation of engineering mechanics. And of course, we go to infinity. And for over a decade, that was our symbol shown on the left side of the screen. Then 2 years ago, I don't know if Arif had anything to do with this, somebody said, no, the lower limit should be minus 250. How many people know why it's minus 250? That's what I thought. I have no idea. Anyway, just a little history there. It's kind of interesting. I thought the 1687 made a lot of sense, but I guess minus 250 also makes sense. This is a little unusual, but I want to dedicate this because I've been at this fund for over 50 years, and I think back about the people that made a difference to me, and I'd like to mention 4 of those today. 3 of those on this slide are no longer with us. My advisor, Carl Allen Cornell, did his PhD at Stanford with Jack Benjamin. His PhD really became the book that many of us have used on uncertainty in civil engineering. Came to MIT as a professor when I was a sophomore, became my advisor for my undergraduate, master's, PhD work, then went back to Stanford, as many of you know. A very close friend, Jared Cohen, convinced me to come to Hopkins, the opportunity to start the department there, then became the Dean of Forestry at Yale, and finally the president of Carnegie Mellon for a decade, who died, unfortunately, earlier this year. And then in Colorado, anybody in mechanics knows the name Casper Willem, a friend and close colleague that welcomed me to Colorado. And finally, since this is sponsored by the University of Illinois Urbana-Champaign, a much younger friend, but a great inspiration, friend of mine, Nick Jones, I hired him out of Caltech for Hopkins. He actually came to the University of Illinois Urbana-Champaign as department chair for a few years, till Hopkins wooed him back as dean, then provost at Penn State, and now the University of Illinois system. So a great colleague and friend. So 4 parts, I said. These are 4 different aspects of how we can apply our knowledge, our expertise to serve community. The first, reliability methods for risk management and resilience on the community scale. When I first got started, we were looking at the concept of structural reliability for simple portal frames for 2 and 3 dimensions, maybe 4 or 5 dimensions. And it occurred to me this same concept of reliability could be used community-wide for a portfolio estimate. And the example we're going to use is San Francisco. So obviously, I don't need to tell you that people that are interested in this are the insurance companies, the community developers, the whole community, and they're interested not in how does one individual perform, but what's the total loss if there's an earthquake, for instance, or other natural disaster. Yesterday at a committee meeting I attended, we heard about the Sim Center at the University of California, Berkeley, and how they're looking at different hazards for communities. And so we're interested in that little yellow part, what's the probability of a significant enough loss to be dramatic to that community? And how are we going to do this? HAZUS was developed to look at the vulnerability of individual buildings and sum them up. Many Monte Carlo simulation methods have been used by researchers to do this. Monte Carlo is a very powerful tool. I think it's wonderful. It's not what I'm most interested in, because I like to look at the mechanics and the mathematics behind what we're doing, although the simulation certainly is a very powerful tool to evaluate this. One thing that simulation doesn't always take into account is the correlation. And as was mentioned with the SimCity, the Sim Center, that we have correlation because of spatial relationship, because of building codes under which the different buildings were done, the soil conditions under area, individual earthquakes versus different earthquakes. If we have no spatial correlation, we get one model, but obviously taking into account correlation, we get very different. And the important thing in the extremes, correlation is tremendous and sometimes not easily understood relationship on the extremes. Alan Cornell used to point that out to me, that when we look at most of the distribution, we can't get away from looking at the extremes, which is where we, interested in structural performance, are most concerned for society. The first order reliability method was developed in the 1970s, very simple, looking at two random variables, looking at a limit state, saying that failure occurs when these cross that limit state. We convert that to standardized variables so we can do it in standardized normal space that changes our variables, but the advantage is we now can look at distance from the origin and use that as a measure of reliability. The advantages of looking at this mathematically is it's analytically correct. With transformations, we use full probability distributions. We include all correlation. And we can look at the sensitivity as we change these parameters, something that doesn't come as easily with simulation. The disadvantage is, of course, we need to mathematically describe everything we're talking about, and there are approximations in whatever we do. So let's apply this very simple concept of safe space and reliability with a limit state to our situation with a community and earthquakes. We need to have a source of excitation. We're using the spectral acceleration, and of course we need to look at the correlation across space, among buildings, and between earthquakes. And so we develop a model of excitation. Then we have to look at the response of the structures, and we were using interstory drift as a basic measure. Again, I don't want to go through the mathematics here. We can either talk about them, you can read about them, but the idea is we now have an excitation and a response, and we can express our reliability in terms of total loss, which is what is interest to a community. The case study that we did was downtown San Francisco. Of course, it has this building inventory, 33 different building types, 33 different occupancy types, designed under 4 different seismic codes, and approximate height of buildings. And we put a scenario earthquake on. Now, what we used to picture with simple portals as 2- and 3-dimensional space, and trying to look at a limit state in 2 or 3 dimensions, we're now 3,000 degree space. Mathematically, it doesn't matter. We can't picture it, but it's the same thing. But now we can apply those simple reliability concepts developed decades ago to look at something as community with 3,000 random variables. We obviously did simulations to compare this. This is one simple example in 3 dimensions. Form assumes a linear failure state. You can do others, but when we look at what really happens, we see that the limit state really is very complicated. And as we look at increasing repair costs, we see that the limit state, even in these simple 3 dimensions that we did here, changes dramatically. So you can imagine trying to picture the limit state surface in 3,000 degree space. So the point is, mathematically, this is a very complicated space, and we can't try to express it everywhere. But by doing this, we can look mathematically at what we happen. We see, for instance, here's a retrofit prioritization. The details aren't important, but it says, for instance, the most dollars should be spent, and this is in downtown San Francisco, mid-rise reinforced masonry buildings built under low codes, in other words, early ones. So this gives us an idea where should we be spending most money, where is it least effective, and that happened to be in concrete frame, unreinforced masonry buildings. But the point is, we can look at the damage to the community and say, where is the community most vulnerable? Where should we put our limited dollars? We never have enough money to do everything we want. I always say a community that has enough funds to do everything at once is a pretty dull community because they can't decide what they really should be doing. But by doing it this way, we can look at how can we effectively use our funds in order to reduce the cost. We can then go beyond damage into resilience. You're all familiar with the general concept of resilience. We can put money into resilience. That is, we can do it so the buildings can be rebuilt and occupied faster. We can have materials available. So now we can do the same thing, but go into resilience. And when we apply that, we now have 5,000 degree space for downtown San Francisco. So we went from 3,000 random variables to 5,000, but we can do exactly the same thing. We can look at total damage and how we can make that more effective. So that's applying very simple reliability concepts now and expanding the idea to what I call big data, the 5,000 random variables, to look mathematically at what goes on in our buildings. Now, that was the first part of my career, although this is a recent study. I hope you younger people here, let's see, oh, that's everybody in the room. I hope you younger people here start thinking more broadly about why society doesn't listen to us. We used to say we have the right solution and we turn it over to society. And some point in my career, I realized I was actually part of society. So rather than turning it over to society, we should be aware of how society makes decisions. Risk perception. Okay, here's a contest. Psychological studies have found that only one group of people have a relatively accurate assessment of the risks they face. These are psychological studies done by Stanford University. All right, how many people think that the group that is best at estimating their risk are insurance actuaries? How many people think it's engineering risk professionals? That's us. Medical? Financial planners? The answer is none of the above. It is individuals who have been diagnosed as clinically moderately depressed. Now think about that. Either the only people in society who understand the risk we face in life are those who are already clinically depressed by understanding the risks they face. And we're fooling ourselves, the rest of us. Or is it just that the people who happen to be good at estimating their risks become medically depressed? So I don't know. There's correlation, but I don't know cause and effect. But the point is, society as a whole does not understand the risks they face. And we're trying to get society to make decisions. We face the quantitative issues, but it's the perceptions of risk. Paul Slovic, a social psychologist, did a principal components or factor analysis and said that the three most important things are the dread people face with events, their familiarity with it, and the degree of voluntariness. I live in Colorado, and every spring semester after spring vacation, at least one student in my class came back in a cast, broken arm or broken leg. They all go skiing. It's voluntary, and they accept that risk. Now, with natural hazards, we don't think of voluntary. I mean, my kids live in San Francisco, and they're both structural engineers, construction people, and they live in San Francisco. They shouldn't, right? But we don't think about that when we decide where to live. So dread and familiarity. Familiarity, something they call memorability. The social scientists have to take regular words like memory and create their own. So memorability is how familiar we are with it, how we can imagine it, and the impact that media has. Media plays up things and is a terrific way to convey to people the risks. On the other hand, they work in anecdotes. They don't work in statistics. The president of the National Academy of Engineering used to say the plural of anecdote is not data. But anecdotes is what people relate to and make decisions. And then dread, the most important aspects with natural hazards seems to be the lead time. For instance, hurricanes versus earthquakes. Much more dread if you can't prepare for it, if you don't know it's coming. And then the scale of the event, how many deaths there are per event, for instance. For instance, here's a comparison of a Hurricane Katrina versus a tornado in Illinois. We don't think much about tornadoes because the number of people affected on each one is small. And for the first time ever, ASE 7 now has some tornado protection in it. We did this, I'm going to actually look at the next slide. What we did is we looked at the main things that people are scared about in different parts of the country. And so we said to FEMA, your divisions in the U.S. are wrong. Your division should not be based on politics. They should be based on what are the major hazards people face. In the Southeast, people are faced with hazards due to hurricanes. And so our message to people as we get across should focus on what is it people are affected by in different areas of the country. Okay, so that's a little bit about the social psychology and perceptions. All right, now I really go off. Let's look at reality. Let's look at how decisions are really made. Forget probability. The public does not understand probability. As a matter of fact, they don't understand mathematics. First of all, there are only 3 probabilities the public relates to. Anything over 90% will happen. Anything under 10% will never happen. And anything else is 50-50. That's the most the public understands about probability. How about mathematics? I can prove the public does not know mathematics. Take out your calculator. It has a percent key. You know, it's not 85% is 0.85 of the whole if it's on sale. It's I got to hit 15% and take it away. They can't do even fractions. They need a percent key. Life cycle costs. No, it's how much does it cost me today? What's the cheapest alternative today? I know one designer that presents his alternatives in terms of life cycle costs because people pick the least life cycle costs then. And psychologically, once you make a decision, it's kind of like hypothesis testing. You won't leave your hypothesis unless the data are overwhelmingly against you. We don't want to be wrong, so whatever we pick first, we stick with it. Optimizations, what's optimization? The public doesn't know about optimization. The mayor of Chicago was voted out because he didn't have enough snow plows for a terrible winter several decades ago. The new mayor came in. Do you think she overspent on snow plows? She sure did, because she wasn't going to get voted out because not having enough snow plows. Was it the right decision? No. Optimally, no. Too much money. But that's where decisions. So we accept that engineering logic is not relevant. All right, here's reality. Public decision maker, you're balancing your limited money of schools, hospitals, etc., public facilities, keeping taxes down. Oh, and one of us, some risk professional, comes in and says, you know, you really should upgrade that bridge because the 100-year earthquake is going to cause a lot of damage. There's a 7% chance that will happen before your next election. Are you going to put money into upgrading that? No, you're going to put money into the new school that you can point to and go do the ribbon cutting and show. Your campaign manager is preparing a list of here's what we can tell the public. You need to be reelected because you know what you're doing. Future deaths, discounting future damages. We have to discount. If you don't discount with lifetimes of 100 years or so for infrastructure, the future dominates everything. But how do you discount loss of life? 10 people dying on a bridge this year, is that really more cost than 10 years from now, 10 people dying on a bridge? Yes, we discount it. Should we? The people on that bridge aren't 10 years older. It's a different cohort. So morbidity, historic preservation, things go up in value with time. Howard Kuhnruther of the Wharton School at Penn calls it not in my term of office. And I call it just incompatibility of lifetimes. Decision makers' lifetime is till the next election. The infrastructure is 50 years, 100 years. Incompatibility decisions. We can ignore that, which we've done. We can build infrastructure for 5 years. No. We can elect politicians for 50 years. No. So what are we going to do? We're going to consider this an engineering problem. How do we help politicians convey to the public that they have made the best long-term decisions for their community? How can we show the results during their term of office? I propose that the ASCE infrastructure report card be expanded to include future obligations, future risks. And actually, 3 different presidents of National ASCE have endorsed the concept. We need to help politicians solve this problem. Give rewards for making decisions now in my term of office for the long-term decisions. A few other issues. Kahneman and Tversky. Kahneman just died this year. First person to ever win the Nobel Prize in economics for the perceptions of economics, not the econometric mathematics, but perceptions. We as a public will spend very little money to reduce the chance of something happening from 50% to 49%. But we will spend an inordinate amount of money reducing it from 1% to 0%. Mathematically, it should be the same. How much money will you pay to reduce the risk of something happening by 1%? But we don't. Risk is not mathematically that 1%. It's, hey, if I can go from 1 to 0, I'll do it. People cannot extrapolate from routine hazards. They go up to Estes Park, Colorado, look at the little river they call Big Thompson, and then I look on the wall of the building way above my height of the flood level that killed several people. And I can't imagine, and I'm a civil engineer, I can't imagine that river flowing at that magnitude. So the public underestimate risk, but we also have what's called social amplification. That is, we create in our mind fears about it. Then you get the social psychologists, these people with risk. True risk, what's perceived by the public. As I mentioned, Paul Slovic tried to look at this. What is it that is a basis for people making decisions? We kill 30 to 50,000 people a year on our highways, but if we're going to put more money, we're going to make those airplanes safer, even though that's the safest way to get from point A to point B. But in case you don't like flying, here's what you can say. Every time you enter the airplane, your chance of death is much higher than every time you enter your car, because the average trip is much longer. We can play with statistics. So should we perceive risk, or should we look at the mathematical risk? There's a whole article, a whole issue of a journal on this, and it had equal number of articles on 2 sides. Let's look at the first one. That's us. We're engineers. Perceptions are not important. Our role is to allocate resources in the most effective way possible, most cost-effective for society's limited resources. That's a nice, easy answer. It's one we usually go to. But the other article said, no, perceptions are important because our role is to optimize the quality of life, make people enjoy life. And if they have an inordinate fear of something, we should recognize that. So we shouldn't ignore it. So my plea, especially to the, as I say, younger people, which is everybody here, think more broadly about the implications of the mathematics you're doing. The Bayesian decisions and such, what does that mean to society? How will they implement that? If we want to rule society, and who's better than us, then we've got to understand how society thinks. Whether we believe perception is important or not, we need to realize that's how people make decisions. And if we want to rule, we have to take that into account. The idea of optimality, I mentioned the mayor of Chicago. Minimax is an accepted mathematical decision-making. It's usually minimize the maximum probability or minimize the probability of the worst event. For a political decision maker, to minimize the number and scale of newsworthy negative events. You don't get elected for being the optimal decision maker. you get voted out by bad events. So we have to recognize that's what people base it on. I'm going to skip that one, but I think there is hope because I think you all can take a more active role in society. I think the public is more willing to accept and understand risks, and they understand their trade-offs in society. The very early in the 1940s concept of structural reliability by Freudenthal said these probabilities will never be real. They're just relative to help us make decisions. But now, with big data, with the sophistication of computers we have, they can be real. And if society is going to make decisions trading off where it puts money, do we get more police? Do we do a hospital? Do we upgrade the bridge? Then these are real trade-offs for society, and we are the ones who can help society make those decisions. Life cycle costing is required now for government buildings. And finally, scenarios and computer visualization can help us convey to the public what they face. Okay, finally, I'd like to end to show I haven't gone completely amok with my social psychology trend, is my most recent research in generalized information theory or evidence theory. I've been advocating probability. I was saying the public has trouble with probability. The trouble with probability is it's incomplete. So let's think more broadly about uncertainty. Very trivial example. We have an urn here with some black and white balls, 50 black and white balls. I don't know how many of each. I'm going to randomly pick out a white ball. What's the probability I get a white ball? Well, it has to be 50% because we have no information to make it greater or lower. That's the least entropy decision we can make, 50%. We have over here an urn with 25 white balls and 25 black balls, well mixed. I reach in, what's the probability I get a white ball? 50%. What was it here? 50%. Probability says those are the same. We get the same answer, 25%, 50% chance a white ball here, 50% here, but there's a lot more uncertainty over here. If we want to bound that, and we have no other information, we have to go from 0 to 100% bound. Bounds of probability are related to generalized information theory. If we have beliefs or evidence, probability doesn't handle that well. Those two situations are different. Or basically, epistemic uncertainty and aleatory uncertainty are different. And probability doesn't handle the two of them equally well. So generalized information theory says, what if we have partial information? What if we have expert opinion? We go in after an earthquake and we tag a building with red, yellow, green tags. That's not a complete analysis. It's expert opinions coming in and looking at that building. Generalized information theory says we can use opinions of experts and combine them without the limits of probability. These are what are called monotone measures, and they're based on degree of evidence that supports our decision. Something like fuzzy logic. Fuzzy logic isn't based on probability. It's based on the characteristics of sets, fuzzy sets. But here it's based on degree of evidence, and that leads to imprecision. This was developed in the 1970s by Dempster and then modified by Schaefer. We're not going to bother with the equations here, but the point is we can use this to look at combining expert opinions in ways that probability doesn't. And we do that because Dempster-Schaefer theory says you must assign belief to the whole power set. So for instance here, not damaged, we have a belief. Moderately damaged, we have a belief, 20% and 30%. Then if you go down to the combined, not or moderately, it's 65%, 15% more. Probability wouldn't allow that. Not damaged plus moderately damaged. The union, if they're not overlapping, can't be more than 50%. So this is uncomfortable to us, that you can get more for the combined event than the sum. But think of it the other way. Start with, I have a 65% belief it's either not damaged or moderately damaged. Of that 65% belief, I'm comfortable putting 20% to not damaged and 30% to moderately damaged, but I don't know where to put the rest. So I can't assign all my belief to the subsets of the power set. Then it makes sense. We can combine expert opinion. Let me just look at the first line here. Event A has a 15% belief of happening. Suppose I have 20 independent experts, but they have the same statistical characteristics, but they're independent statistically. If each one believes 15% for event A, and they all believe 15% because they're statistically identical, although they're statistically independent, then probability theory says if all 20 experts assign a 15% belief, then 15% is the probability. I have a lot more confidence, lower confidence limits, but the expected is 15%. Belief theory says if you use Dempster-Schaefer, that goes up to 92%. In other words, it says if 20 experts each believe there's a 15% chance, their belief, they all contribute some belief, and together it becomes 92%. Now, which is right? Which is correct? There is no correct. Probability limits us to saying 15% is my belief, if 20 experts said that. Evidence theory says, well, wait a minute, if 20 experts all believe there's a 15% chance it's happening, maybe there's a 92%. And of course, we can do in between by weighting and all. But that's the broader way of looking at uncertainty. So finally, let me say that engineering risk professionals can provide information on the incompatibilities of lifetime, political versus infrastructure, the deceptions of return periods. So people didn't understand a 1% annual probability of a flood. They can't do that, but they can understand a 100-year flood. Now the world thinks it happens once every 100 years with certainty. So we've given the wrong concept. Return periods were a way to try to communicate with the public that didn't work. Government regulations, State Farm wanted to pull out of home insurance in Florida after a bad year, and the state government said, fine, but then you can't insure cars where you make all your profits. So we can develop communication tools to help this. Structural reliability, the mathematics, our engineering expertise, risk assessment, those are tools and those are important and that's what we can provide. Let's just remember that's not the end of it. So I know we don't have time for questions now, but I will be around obviously for the conference. I thank you so much for coming, for the opportunity to do this. It's been a wonderful career. When I started, we never mentioned probability in the codes or uncertainty. We hid it. And so what I've seen over the past 50 years is where society says what we do is really crucial, and we need to be part of society. Thank you so much.